Welcome, everybody. That's the first session of Fast Nordic, and we are speaking about optimizing DAX queries. As usual, before I start speaking, I want to understand something about you. Just a few questions, which are, how many of you already used the DAX language? Well, more than half, which is good. How many of you have used it to create queries and query data model with reporting services or other kind of tools? Thank you. How many of you had problems with the performance of DAX? 2. So why are you here? We are going to speak about how to optimize DAX query. That means getting better performance out of DAX. It will not be easy. DAX is incredibly fast. But if you start loading billions and billions of rows in fact tables and run complex queries, of course something happens. A few words about myself. I'm Alberto Ferrari. With Marco I founded the SQLBI.com website. You can find there all what I write or what I think about DAX, tabular multidimensional analysis services. I specialize in business intelligence and the DAX language. So today my main interest is in DAX, the tabular engine, and large implementations with the in-memory database. I'm a book writer, BI partner, SAS Maestro, and MCP, and a lot of different names. But I'm not here to sell myself. I'm here to speak to you about tabular, about DAX, the query architecture of DAX, so how it works, how DAX is able to run so fast, and what are the engines that live inside the DAX engine, and then how to use the profiler in order to get the best out of it. The main interest will be in the in-memory mode and vertipack. You probably know that a tabular engine can run in direct query mode or in memory with the vertipack engine. Direct query is slow. It doesn't work as we might expect. I cannot say all the words we are recorded, but I'm not going to speak about direct query. I'm just going to speak about in-memory mode and the vertipack storage. And I hope you have some understanding. How many of you know how vertipack stores data? Well, some of you. For the ones of you who still don't know that, go and study it. It's very important. Understanding how vertipack stores data and how the engine organizes information is really, really useful in order to understand how to optimize the engine and how to optimize the data model. There is a session from Marco this afternoon that speaks exactly about how to optimize the data model using your knowledge about how data is stored. So in the agenda today, I will try to explain you how to understand the best way to optimize a query, how to use the profiler to understand what the engine does when a query needs to be resolved, and how to solve a performance issue. Solve performance issue means understanding to which extent you can go in optimizing a query. I'm not going to show you how to take a query that runs in 10 seconds and make it run in half a second, because that's not real world. In the real world, you speak about percentages. You try to cut 20% out of a query. You try to cut 30% out of a query. You try to increase the cache usage. This is what you need to do if you run a large system with thousands of users querying the system all the day. And so you need to get the best out of the engine. What I will try to teach you is, do not trust best practice. Best practice are fine, best practice are useful. If you follow best practice, good chances are that you will not make too many mistakes. But you cannot just cheaply follow best practice. You need to understand why a best practice is a best practice, so that you exactly understand why you should do things in one way or the other. So what I normally try to teach people is, remember that best practice are just hints. They are not rules, they are not written in stone. You are free to change all the best practice if they fit your model. And the first thing we need to understand in order to start our journey in the DAX engine is the difference between formula engine and storage engine in DAX. So again, another question for you. How many of you know what the formula engine and storage engine are? Same two of before. This is very, very important. The terminology formula engine and storage engine comes from multidimensional. There we have storage. Something was written on disk, need to be grabbed from the disk before processing. And so the storage engine was responsible of loading data from disk and make it available in RAM so that the formula engine could compute values over this set of data. In Tabular, there's nothing like it. We don't have storage. Everything is in memory. Yet we have formula engine and storage engine. The formula engine is an engine which is able to compute complex expressions. If you write an if statement, if you use VLOOKUP, if you use summarize, if you use many of the advanced DAX functions, then formula engine is the engine which is able to understand and work on these formulas. Storage engine, on the other hand, is responsible for fetching data from memory and doing processing on this data. It is incredibly fast. It is multi-threaded, so it's able to scale over many cores in a very efficient way, but it is very limited. It doesn't have the full power of DAX. So storage engine is able to do simple sum, it's able to do simple math, can multiply two numbers, can follow a relationship, but it is not able to understand more complex queries and more complex expressions. These two engines, you can think of these two engines are as two friends working together in order to solve all of your queries. I stole this slide from a session that somebody from Microsoft was delivering, I guess, at TechEd a couple of years ago, that describes the difference between storage engine and formula engine. Storage engine is, formula engine, the DAX language, is very rich, very powerful, but it has a very strong limitation. It is single-threaded. So no matter how many cores you have on your box, if you use formula engine, only one of them will work at a time. And so there is not much space for improvement of speed, because only one core is working and you don't have any hardware option. The storage engine is completely different. It's multi-threaded. It can scale on many cores. Remember that in Tabular, many cores means 6, 8 cores. It's nearly impossible to get good performance with more than 8 cores. But it's a very simple engine, so it does not know everything which is needed. This is how Microsoft explains formula engine and storage engine. In my mind, I use a completely different picture. I think that formula engine is a rich engine designed for expressivity. It's able to understand a lot of things, while storage engine is his brother, which is not as smart as formula engine, but it's damn fast in doing calculations. So, why all of this is needed in order to optimize your queries? Well, for one reason. Optimizing DAX means trust the Rain Man. Try to move all the calculations on storage engine and try to remove calculations from formula engine. Whenever you hit formula engine, you have the one core limitation, you have a slower engine, you have a lower cache usage, you have a lot of issues when you use formula engine. On the other hand, when you use storage engine, you have many cores, you have full cache, you have a faster engine. So optimizing DAX, the first step in optimizing any DAX query is always take the execution plan from the formula engine and move it to the storage engine. Once everything is in the storage engine, then you can start further optimizations, reducing queries and try to remove slow part of the code. But of course, all this raises one more question. How do I understand and how how do I know which part of the query is executed by storage engine and which part is executed by formula engine? Because this is the core of what you need to know to optimize the code. And so it's time to start going deeper in the engine and understand more about what happens when you run a simple query. And to understand the query, to understand what happens inside the engine, you have only one tool, which is the SQL Server Profiler. Using the profiler, you can grab the query plan from any DAX query, understand the query plan, and then follow an optimization path, which is what we will do. Understanding the query plan is not as easy as you might expect. If you are dreaming about a query plan like the one of SQL Server, a graphical representation of your query plan with arrows and with a lot of useful information, stop dreaming, because this is absolutely not something sexy like the SQL Server query plan. It's much more rude. It's just a long string with a lot of information inside it, yet it's the only thing we have available. And it is much more than we have with MDX. With the MDX language, there was no way at all to understand what was happening inside the engine. With DAX, at least, we have a query plan that we can use. And there is not only one query plan, there are many of them. Basically, there are two different query plans, the logical query plan and the physical query plan. The logical query plan shows, in reality, it shows the grammar tree of the expression containing all the operators that need to work in order to solve a specific query. It does not clearly indicate the execution path. It's just a logical representation of a query. The physical query plan, on the other hand, is a very precise representation of what happens inside the engine, but it's harder to understand. And using the physical query plan, you will understand exactly how each step is executed. And finally, we have vertical queries. Vertical queries are queries executed by the storage engine to retrieve data and return them to the formula engine. So there are three different items we need to understand. The logical query plan shows the grammar of the query. The physical query plan shows the actual execution path of your query, and the vertical queries are the fetching of data from the storage to compute values. What happens when the optimizer starts to work on a query? It does a lot of different steps. First of all, it takes your query, checks for the syntax, checks that everything is fine, and builds an expression tree that contains a different representation than a string of your query. Then it needs to start optimizing your query. You wrote a query, that query contains several statements, several function calls. The optimizer needs to make its work, which is finding the optimal query plan. And to do that, in order to build the optimal query plan, DAX needs to understand how many rows will be returned by different parts of your query. This is the same that happens in SQL Server. If you are familiar with SQL Server query plans, SQL Server uses statistics to forecast the number of rows that will be returned by specific parts of the query. Tabular is much more precise. If it wants to understand how many customers have a specific name, it runs a query against the database, grabs that number, and then it knows exactly how many rows will be returned. So, during the optimization process, there are a lot of queries that are executed by the optimizer just to understand how many rows will be returned by different parts of the query. Once all these queries are executed, at that point, the optimizer knows the optimal query plan. And only at that point, it fires the logical query plan. It shows the logical query plan in the profiler. Then it goes on executing. During execution, it runs again many vertipack queries, many queries against the vertipack engine in order to retrieve data, and executes the physical query plan, which is fired near the end of the process. All these events, the logical query plan, the physical query plan, and the vertipack queries are events that you can grab using the SQL Server Profiler to understand what happened inside your query. Remember that DAX is not like SQL Server. SQL Server is a cost-based optimizer, meaning that it has many different ways of executing a query, and using statistics, it understands which of the many ways of solving the query is the most efficient one, the one that costs less. DAX is not cost-based. It's expression-based. You write an expression, and this expression will always have the same query plan. The only reason why it needs to understand how many rows will be returned by different parts of the query is to move filtering deeper inside the vertipack queries or in the outer part of the vertipack queries. So it's just a matter of filtering before or filtering later, or choosing a different path for joins. But the query plan is always the same. So if you optimize a query on a data model which has 1 million rows, you will have the same optimization running for the same data model with 10 billion rows. There will be no difference. But remember another important thing is that DAX optimizes the complete expression. It does not optimize only the query you write. So if you write a measure and this measure is very complex, it might be the case that the query plan for that measure is different if the measure is used in different queries. Because the measure is put inside the query, the complete tree is optimized. And so one measure can have different query plans depending on the usage you do. It's not unusual to optimize a measure, then run it inside a query and see that it is slower than a previous version which was slower in a different query. So always try to test the complete query because it's very important to get the best performance. Now, using the SQL Server Profiler, I guess, are you familiar with the SQL Server Profiler? Yes, most of you. So all you need to do is open the profiler and select the right set of events from the set of events that you can grab from analysis services. Basically, you need to catch, and we will see that in detail, but there are events which are important. Basically, what you need to grab is the query end event. I always take the end event. You always have a start event and end event. The start happens, as you might expect, at the beginning, and the end at the end of a query. I use the end because it already contains the duration of the query. At the beginning, it's unknown. At the end, Tabular knows how much time it took to run a query. So I normally take the query end event, the DAX query plan, and the vertipack storage engine query end. The query plan shows the query plan, the query end shows the complete query, and the vertipack query shows the queries executed by the vertipack engine. Vertipack is just another name for the storage engine of analysis services Tabular. And so, in order to understand how things work, let's start with a very simple query, the simplest one you can imagine. We will monitor this query, which is just evaluate raw result that computes the sum of internet sales amount. As you might expect, there is not much that we can do to optimize such a query, but it's useful to start looking at how to read a query plan. We already have, can you read it from the bottom? Yes, okay. This is a query that we can run against AdventureWorks. It will be very fast, of course. But what we want to understand is what happens inside the engine. To do that, we need to use the profiler. You create a new trace on analysis services. I have already created a template, DAX query plan, that contains my events. We have query end, DAX query plan, vertipack storage engine query cache match is useful to understand which queries are resolved by the cache, and the query end that shows the end of a query. So you can create your own and then save it so that you don't have to select all the events every time. Now the profiler is running, waiting for some query to be executed, and we run this query. It executes, gives us a number which doesn't have much sense. What we wanted to see is what happened here. We have the first event is a DAX query plan, which is the logical query plan. If you look at the logical query plan, it's a string, nearly impossible to read, that shows the structure of your query. Add columns, sum vertipack, scan vertipack, and then the internet sales table, which is the one scanned. Basically, there is a scan of the internet sales table and then a sum happening inside vertipack, and then add columns returns the final result. The logical query plan is not really useful unless your query is very complex, because it just shows the structure of your query. Then you have different vertipack queries. I guess you remember, vertipack is the storage engine, so these are queries executed by the storage engine to retrieve data. And there are always two, sometimes 3 or 4, but many queries with the same shape. There is a vertipack scan and there is a vertipack scan internal. You will see a lot of them, they will have the same code. This is the vertipack scan internal, and this is the vertipack scan. It's the same code. What happens here? Formula engine needs to grab some value, so formula engine asks to storage engine to run a query, and it sends a vertipack query. Storage engine takes the query, and knowing a bit more about the internal structure of your table, can slightly change the shape of the query to make it run faster. Sometimes it adds a measure to the query, sometimes it decides to use one data structure versus another one. But basically you will always see two of these queries. You don't need to worry too much because they are in reality the same query, just two different versions of the same query. And you are not using the sum of the time of the two queries, you are just using the sum of the one, the internal one. The other one is just for reference. So this is a query executed by the engine, and you see that the query looks like SQL. It selects sum of internet sales amount from internet sales, which is the number we requested, the sum of sales amount. And then we have the physical query plan. The physical query plan is slightly different from, no, it's not slightly, it's completely different from the logical query plan and shows in greater detail what happens inside the engine. There is the innermost part is the vertipack result. Formula engine takes the result of a vertipack query and then does further processing on it. What it is doing here is take the result of the vertipack query we have seen before, which already contained the sum of sales amount, and then it really does nothing, because it aggregates from the cache, it searches for the only value that exists, creates a table with a single row, and creates a row containing the result, which has that single value returned by the engine. So it's not doing anything, formula engine in this case, it's just grabbing a number which has been computed, and then it is returning to the coder. This is a very simple query, but you have seen that for a very simple query, we already have a lot of events we need to analyze. And then finally, you have the query end that shows the complete code, and most important, shows duration and CPU time. Duration is the time needed to execute the query, 44 milliseconds. CPU time is the amount of CPU used. In a multi-core system, you will always have CPU time longer than duration, because I can have 10 seconds of CPU, but since I have 10 cores, the duration is only 1 second, because it runs on 10 cores in parallel. Now, this query was very simple. But if you run a slightly more complex query, like this one, here we are doing something different. we're doing a summary of internet sales by province name, so I will get all the province names, and for each province I add the sum of sales amount. So that's a sum of sales amount grouped by state province code. Not for all the customer, but only for the customer whose name is Anand. That's a very simple query again, but slightly more complex than the previous sum. We are not going to optimize this query. I just want to show you what happens in the profiler when you run the query. We clear the profiler and we run the query. We get the result, which shows for each state the amount sold. And this is what happened in the profiler. You see that we have vertical queries executed before the query plan. These are queries that the engine runs in order to understand how many rows will be returned by parts of the query. There are always pairs of queries, and if you look at it, it's a select state province name from internet sales, left outer join cost customer and geography, where customer last name equal Anand. So basically, this is computing the state province names that exist for the customer whose name is Anand. It's a very fast query, it runs for only 2 milliseconds. Once Tabular knows this information, it is ready to create the query plan. I'm not going to do analysis in detail of this query plan, just because this is not very interesting to optimize. I just want you to show the kind of job you need to do if you plan to optimize something. Once the query plan is out, then it starts running other queries. Here we have another query, which is select the state province name, this time with the sum of sales amount. So it's a different query than before. Now we get the state province name and the sum of sales amount from internet sales, left outer join customer geography. This is a vertical query, and you see that it contains simple mathematical operations and simple joins between tables. Then we have this query returns the state province name and the sum of sales amount. We have another query that returns the state province names. So at the end, Tabular will have two different sets. One with state province name and sales amount, and the other one with just state province name. And Formula Engine will do the last job of doing the merge between the two data sets to produce the final result. This second query runs on the cache, because this query has the same shape as this one. It's exactly the same query, and you can see that on the bottom nothing changes, sorry, if I go from one to the other, because it's the same query. The first time I executed it to understand how many state province names existed. The second time I executed again to get the real state province names, and at this point I don't have to execute it again because it has been cached. Finally, the query plan does iterate over two different result sets. There is this vertipack result and this vertipack results. This contains 21 rows and this other one contains 21 rows. The first one contains only the state province name. The second one contains the state province name and a currency column, which is the sum of sales amount. And Formula Engine does the job of merging these two together by using add columns. But it is doing iteration on only 21 rows, and as you might expect, it is very fast in doing it, because the resulting set is very small. If you don't see millions there, then your query plan is very good. When you see tens of millions of rows being scanned by Formula Engine, then it's time to rephrase your query to reduce this amount. And finally, the full query is executed in 10 milliseconds, which is very fast. You see that, for example, this vertipack scan internal has 31 seconds of CPU time, but only 31 milliseconds of CPU time, only 2 milliseconds of duration, because it was executed on many different cores, and so it runs very fast. Let's do a quick recap before we start looking at more complex code. What's that? We solved this query. Then we try to follow this other query, which is slightly different. And for such a simple query, we had to run one vertical query to get the number of state province that satisfy the filter, then a second query grabbing the state province. Finally, we have the DAX query plan, the logical query plan. In red, I highlighted the vertical part of the query plan, that is the fast part, the part that is executed by the vertical engine and runs very quick. As a rule of thumb, whenever you see vertical, that means you are on the fast side of a query plan. Whenever you don't see vertical, you have to worry about it. If you look at the query plan and the query side by side, you see that they are more or less the same query. We have scan vertipack, group by vertipack, where we have summarize and group by state province code. We have sum vertipack, where we have sum of sales amount. So they are exactly the same expression. Sometimes for very complex expression, it is useful to look at the logical query plan to get a first understanding of the query. But then, if you want to optimize, you need to go at the vertical query level and start playing with it. And then you have the query running. The first query is grabbing the complete value, that is state province code and sum of sales amount in the same result set. And the second running query is only taking the state province code. Now I have two sets, one with the state province code, the other one with the sum. I merge them together and I produce the final result. So a very simple query plan produces something like 4 vertical queries, 2 before the execution and 2 during the execution. All intermediate results are cached and then used by Formula Engine, and the final join is executed by Formula Engine. Why I think it's important to take a look at such a simple query? Because if you think that you can start taking your DAX query containing tens of measures and a complex summarize that feeds data on the reporting services report and start optimizing it, you are not doing it right. Because optimizing DAX means starting from a small expression and then understanding how to optimize each piece. And once you have a good understanding of the small pieces, then you can go over complex expression. I have customers that send me queries which are 3 or 4 pages long, asking me to optimize them. It is good, but you need to understand that to do that, you need days of work. Take the query, understand what it does, look at all the vertical queries, get a sense out of them, and then start modifying small points in the query, knowing that whenever you touch something in the query, the complete plan can be changed. And so you need to start again and again until you get good results. And this is what we are going in the second half of the session, when we start playing with queries. We have already seen that you have CPU time, you have duration, you have the event subclass, and CPU time is always greater than duration, because many cores run in parallel on the same engine. This happens only for vertipack scans. Formula Engine does not use many cores, it only uses one core, because Formula Engine today is single-threaded. Speaking about optimization, it is important even to understand how the cache works. Because you have a query plan, you have already seen that sometimes a vertical query is resolved by the cache. So it's interesting to understand what does DAX caches. DAX caches the result of vertipack storage engine queries and nothing else. DAX does not cache the final result of your query, but only the partial results of vertipack queries executed by the engine. So if you use a storage engine, that is, you have complex vertipack queries running very quickly in multi-core environment, you are also using the best cache, because you are using cache of a storage engine. The result of Formula Engine is not cached. So if your query runs for, let's say, 1 second in storage engine and half a second in Formula Engine, that final half a second will always be paid whenever you run the query, because the first second of storage engine will be answered by the cache, the second part, Formula Engine, will not be answered by the cache.
If you use MDX to query tabular, then the cache is slightly better because you have even caching of measures and the MDX cache is available. Sometimes it is better to use MDX, sometimes it is better to use DAX. Generally speaking, with DAX you have a finer control over the algorithm used, so you can express better expressions. With MDX you have a better cache. And you need to remember, of course, when you run performance tests, to always clear the cache. Otherwise, the results you see will be wrong. That doesn't mean you always need to optimize everything with cold cache. You need to know the cache, understand the cache, and think how to get the best usage of the cache. In a multi-user environment with thousands of users running, the cache plays a very important role. So you need to run the query on cold cache, on warm cache, and see the difference between them. Now, let's start looking at different query plans, how to work with them, and how to understand them. The first example, I don't want to use the slides for this example. I prefer to show them using the code. I just need to find a very simple expression. Okay, this way you can read it. We already know what the query plan of this query will be. That's just the sum of internet sales amount. We go to the profiler, clear it, then we run the query, and we see our result. We executed the query using just a few seconds ago, so we have a cache match for the vertical query, and the query is executed very fast, very, very quickly. Everything is inside storage engine. Now, let's try to write the query in a slightly different way. I need just to make it a bit larger, otherwise it will be impossible to read it. Okay. This time I do a sum of sum x over internet sales. I hate indenting things. Yeah. Well, now it's much better. You know, the power of a keyboard. This time the expression is different. Instead of running oh, that's, of course, it's a wrong demo. What I wanted to show you here is iteration happening. So I wanted to query this query to be this way. It's always beautiful when the speaker makes a mistake. Now, the result is not sum of internet sales. We already knew what this query would return. We do a sum x over internet sales, getting the sales amount. So we are doing iteration now. And you might expect, or you should know, that sum x iterates over the table. But if you run the query, let me clear the profiler and run again the query runs very fast. And if you look at the events, we have the logical query plan, and then a vertical query. The vertical query is select sum of sales amount from internet sales. So there is no iteration. The query sum x over internet sales has been resolved without the formula engine doing anything, but just running a sum in vertipack over the storage engine. So this is why sum x in this case is very, very fast. Tabular knows that vertipack is able to do simple mathematical operation. But if you rephrase the query in a slightly different way, in this way, for example, you evaluate raw result, you do again iteration over internet sales, but this time the expression is a different one. You check if internet sales is greater than 0, then sum it, otherwise skip the row. Now, inside the iteration there is an if, there is a condition. And the condition is too complex for the Rayman. It's not able to do a simple condition. And for this reason, you will see the query plan completely different. If you run this query, let's clear. The result is again very quick, but this time the vertical query has a completely different shape. You see, it's sum of callback data ID if internet sales amount, then internet sales amount. Now, what is this callback data ID? DAX understands that it is not able to compute that if. And because it is not able to compute that if, cannot make the query and cannot let only storage engine answer the query. So storage engine will iterate over the table row by row, and for each row it will do a callback to the formula engine, asking formula engine to evaluate this expression. And so in a query like this one, you have both formula engine and storage engine working together on the same query. And in this very special case, you will have one instance of formula engine for each thread of storage engine. So it will run in parallel even if formula engine is used by your query. If you want to take a look at how callback data ID work, you can think of the storage engine scanning your table row by row. It goes on the first row, take the sales amount and the quantity, do a callback to the formula engine, ask formula engine to evaluate the expression, get the result, and store it as the result of the first row. Then goes on the second row, does the same operation, grab the result, and put it aside, does it for the third row, do the computation, and do the final sum. So the aggregation is computed inside the Vertpack engine. There is no memory usage, but there are many instances of formula engine being called by storage engine. Now all these, there is next slide which is useful. From the performance point of view, whenever you see callback data ID, performance is lower. You don't have the best performance of Vertpack, yet it is pretty fast because pure formula engine is single-threaded and not cached. Callback data ID is multi-threaded, yet it is not cached. Because remember, the only thing that is cached by storage by Vertpack is the result of Vertpack queries. Whenever formula engine is used, there is no cache working. All the queries we have seen up to this point run on AdventureWorks, and it's really hard to see bad performance on AdventureWorks. So in order to see the cache usage and to start playing with the cache, we will use a different data model that contains a few dimensions. I'm not interested in the business rule of this data model. I only want to have some rows to run the queries. We have dimension with not so many rows. We have a bridge table with 2 million rows. And then we have 4 billion rows on the fact table containing references to networks, calendar, time. This is audience analysis of television broadcast for a customer. So instead of running against a few thousand rows, we run with 4 billion rows. And of course, performance will be different. We will be able to see duration and to see some numbers. So we do a first test. This is the sum of audience weight. Weight is a column on my table. I need to change the connection to audience. We run the query, which is computed just the sum. And we don't want sum, we want sum x over audience, of audience weight. We go clear the profiler and run the query. Of course, this is going to take a bit more because it's scanning 4 million rows. We know it took for 2 seconds to scan it. And if you go on the query plan, now the information is slightly more interesting because you see that we have the DAX query plan, the Vertipack storage engine query, which is, as you might expect, select sum of weight from audience. Everything is computed by storage engine. The duration is 12 seconds, but because the storage engine runs in a parallelized world with many cores, the real duration is 1.5 seconds. So 12 seconds were parallelized in order to get only 1.5 seconds. And the final duration is exactly the same. So everything is computed in storage engine, there is no formula engine working here, even if we have iteration. If you do the same query using introducing callback data ID, look at this query. I just need some more space. The number 300,000 has no meaning. I just sum from the fact table, doing a condition: if the weight is greater than 30,000, then compute it, otherwise keep it. The condition is just there as a placeholder to see sometimes you have more complex conditions in your code. If you run this query, remember the first one was 1.5 seconds, and you look at the query plan. Oh, here we have task manager. This is formula storage engine working, so all the cores running together. And if you go looking at the scan, you see that it is completely different. The Vertipack query now is select sum of callback data ID. If the weight is greater than 300,000, then compute the weight, otherwise do the callback data ID. Skip the row. So this time you have storage engine calling formula engine, the two are working together, but the price of the callback data ID is very, very high. And you can see that this query runs in 11 seconds. 84 seconds is the total CPU time, which is parallelized using 10 seconds. So the usage of formula engine inside your query has a huge impact on performance, which you don't see if you run on VentureWorks. You need large databases in order to start looking at the difference. At this point, you might wonder how to optimize this query. Remember, the goal is remove code from formula engine and put the same code on storage engine. So let storage engine compute everything and avoid formula engine. Even because if you run this query again, we run it again, and you look at the CPU usage, you see again 100% for 10 seconds, because we are using formula engine. Formula engine is not cached. So whenever we execute this query, we will see 10 seconds of CPU usage for the execution. How can you optimize such a query? Well, instead of doing the condition, doing the test inside the iteration, you can take the test and put it outside of the iteration. And so you follow a best practice, which is use calculate, compute the result as calculate sum of audience weight, where audience weight is greater than 300,000, which is a different way of writing the same query, but the final result is exactly the same. The difference now is that there is no operation happening inside iteration that needs formula engine kicking in. We don't need to clear the cache now. We can run this query and see if we have some benefit. I need to clear the profiler and run the query. In the meantime, we take a look at the CPU usage. You might expect this query to be very, very fast, but unfortunately, this is not yet the case. Even if I would like you to note that the pattern now is completely different. Before we had 100% of cores for 10 seconds and then a stop. Now, if you run the query, you see 100% CPU for some time, then a drop, then again 100% for a smaller amount of time, and the final execution. So it's clear that the execution path is different. but we have the profiler that will tell us everything about this query. We have a first vertical query, which is using 9 seconds, and this vertical query is selecting the weight from audience where the weight is greater than 300,000. So the first query, which is using something like 9 seconds, is querying only for understanding which values of these columns are larger than 300,000 to evaluate the condition. Then, once the query is executed, you have a second query which selects the audience weight from the audience where, and look here, audience weight in, there is the list of all the possible values of the weight which are higher than 300,000. So what happens here is that Tabular builds a bitmap on the weight column, which is our condition. Building the bitmap takes something like 10 seconds, and only after the bitmap has been created, it can scan again the fact table to compute values and grab the final result. If you were to optimize such a scenario, the best place where to work is, of course, this condition. You need to remove code from the condition. You already did something good, because if you run the query again, because now everything is computed in storage engine, you see that the query returns immediately. We have the number, and instead of taking 12 seconds, it took half a second to run the query, because all the results are cached by Vertipack and you get an optimal usage of the cache. Yet on cold cache, this query is running very slow. Now, let's try to do a simple test and ask ourselves, is the problem in the fact that we are filtering a column of a fact table, or is the problem in the expression? If we change this query, and instead of using greater than, we use equal to on the same column, and we run this query, it runs incredibly fast, and there is no cache here, because this is the last query. We have select audience weight from audience, and then select with a single query running for half a second, we have this text. So, looking at these query plans, look at how the query is resolved, you can understand exactly what happens inside the engine and where you can improve things. All this exercise should lead you to one of the easiest way of optimizing a DAX query, which is if you have a complex condition like this one, you can obtain a boost in performance by removing the complex condition from the query and materializing the condition as a bit on the fact table that already computes the condition, which is a complex one, stores it inside the fact table. It's a single bit, so it doesn't use a lot of RAM. And when it will be time to run the query, instead of evaluating the condition for each row, which is the most expensive part of the query, you simply run the query. You query using an equi condition. The second example that I want to show you is the difference between summarize and add columns. One of the best practices says that it's better to use summarize instead of using add columns. It's best to use add columns instead of summarize when running a query in DAX. And so the idea is whenever you can, avoid summarize and prefer add columns. How many of you know about this best practice? Always the same, 2, 3 now. How many of you know why it is best to use add columns and not summarize? You are lying, because I tested yesterday. Marco is lying now. We will try to understand it. Let's take a very simple query. We do a clear cache, which is always a good thing to do. Look at this query. Let me just increase the font. That is very, very simple. Evaluate, summarize from the fact table, doing the grouping by individuals. Think at individuals as customers. So I count the number of rows in the fact table, grouping by the age range of the individual. And the query is just count rows of audience. I take my query, I clear my profiler, which is taking too much space. I run the query. It gives an error because I need to go on the right database. Runs for a few seconds, 3 seconds, and I get the result. I'm not interested, as usual, in the result. What I'm interested in understanding is what happened in the engine to answer this query. And we have it here in the profiler. Reduce space here, increase it there, do a zoom, and here we go. We have the query plan, and then 2 vertical queries. The first one is selecting individual's age range from the fact table. So we are starting from the fact table, doing a join with the individuals and grabbing the age range from the individuals. And this is taking 1.2 seconds. Then we have a second query, which is selecting the individual's age range and the count from the fact table, doing a join with the individuals. That's very similar, 2 similar queries, but you will see this pattern many, many times. We select first a table on the left, a table on the right, and then the final join is performed by Formula Engine. We have 1.2 seconds for the first query that selects only the age ranges, and 1.6 for the age ranges and the count rows of rows. Now, if you look at the result, the number of age ranges is in the orders of 10, 12 different rows. It looks very strange that it takes 1.2 seconds to retrieve 12 values for a join. The problem is that in the query plan it is clear that the list of age ranges is taken from the fact table in join with the dimension, and the fact table is 4 billion rows. It would be good if we could instruct tabular and says, listen, when it's time to grab just the age ranges, don't look at the fact table, just take them from the dimension, which is smaller. In this way, we will improve performance. And we can do that. We do a clear cache as usual, so we don't have issues. And now we use add columns instead of summarize. We do add columns over the values of individual's age range. If you write values in the individual's age range, there is no fact table in the middle. And so you are telling DAX, grab the individual's age range from the individual's table, and for each one of them, compute the number of rows in the audience table. You run this query again. We get the result, and here we have the second query plan. We have 1.2 seconds for the first vertical query, which is taking individual age range and count of start from audience. And then we have another query which is taking 0 milliseconds, which is computing individual age range and count from individuals. The difference between the two is that this is taking twice 1.5 seconds, this is taking at the same time only once. So we cut by half the time required for the query just because we moved the scan in the right table. Now it is clear that you will not always be able to cut by half the size, but looking at the query plan, you can look at the query, understand what happens inside the plan, understand what DAX does, identify the places where you want to cut some time, and try to rephrase the query in such a way that you avoid the most expensive part. you can understand how much you will gain from the query. In fact, if you run for a more complex query, like a distinct count, you will see that the summarize using distinct count is taking instead of sum, we use summarize, and it's taking 6 seconds. If you run the same query, but instead of using summarize, you use add column after having cleared the cache, then you will not see half of the time, because the distinct count part is always the same. You are only saving 1.2 seconds for the scanning of this table. And so the query is using 6.4 seconds. Using add columns, you have 4.8. If you don't understand why add columns is better than summarize, you can have different expectations. While if you understand exactly what you are removing by using add columns instead of summarize, then you know which part of the query will get an improvement and which one will not get an improvement because you are not touching them. Then distinct count can be further optimized using different techniques, but this is much more complex. Let me skip the last examples that I were supposed to skip. I always skip some slides at the end in case I run too fast, which never happens, but you know, better be safe. So, let's go to some conclusions. DAX, as you have seen, is not easy to optimize. If it was easy, that it would be boring and not very interesting. It is hard, so it's interesting to optimize it. It's much better than MDX. MDX was a black art. There was no way of understanding what happened inside an MDX query. Whenever I think at MDX, I think at my wife. I ask her, honey, is there a problem? Silence. Then you try it again, honey, is there a problem? You should know that. And that's all what you get as an answer. DAX is much better. It tries to tell, it tries to speak and to tell you with the query plan exactly what's happening. So if there is a problem, you can ask and say, yes, the problem is somewhere here. Go and find it by yourself. But at least you know that there is a path that you can follow to optimize. It's not easy, but it's incredibly fun, at least for me. Do a lot of tests. Don't just follow best practice. Try to understand exactly the shape of your query and then understand how to get the best of it. Never trust simple rules like do that instead of this, because DAX is several times surprising. That was the last part. Thank you very much for attending. If you have any question, of course, I'm still here and I will be around today to answer any question or anything you might have to say. Thank you.